my name is Chris. I'm a web developer here in Toronto, and I'm going to talk about state machines. I'm sure, how many people know what a state machine is? Nice, most of us. Okay, so I'm hoping with my talk today that all of us can learn something, get a little takeaway. Maybe you'll learn a bit about state machines, maybe you'll learn a bit about something else, we'll see. So this is the overview, this is what we're going to go over today. So just to start off, why learn about state machines? So they can give you insight into your code. Maybe you've written it, maybe someone else has written it, and it's complex, and you don't know all the code paths. If you try to model your code as a state machine, you get a bit of insight into what all the various states of your code are, and how your program goes between each of those states. And that leads to the next thing, testability. If you know all of these states and their transitions, you'll be able to test them easily, and you can't test what you don't know. And if for some reason you need to prove the correctness of your program, a state machine is a mathematical concept. You'll be able to prove it mathematically. So that leads into the mathematical notation. I just pulled this from a PDF online. I don't know what TAWACIL is, but they have a good slide. So when I was in school, I had this drilled into my head. DFA is a 5-tuple. So that's just an easy way of saying there's 5 things that make up a state machine. One is the states. The alphabet, so that's like the input that your state machine can accept. The transition function, so this takes your current state, the input, and then returns the next state. And then it also has a start state, which is how your state machine is initialized, and then also has a set of accept states. Some of the examples tonight will have accept states, some of them won't, and you'll see why, I guess, with the examples. So that leads us into a simple example. So we want to make a state machine, and our goal is to determine whether the number of zeros in an input sequence is even or odd. So this is a pretty classic application of state machines. Just do some simple pattern matching within a string. So our alphabet will be 1 and 0. We're just going to say if it's even or odd. We'll just look at which state it's in, so there are no accept states. And just for clarity, if we have 0 zeros, it's even. I know there's some debate about that, but we're going to go with that. So this is a simple state machine. I know the loops are a little weird. It's hard to do a good loop in diagramming software these days. So if you know diagramming software where you can do good loops, let me know. So the start of a state machine, you can tell by usually the start symbol or an S with an arrow leading into the first state. So in a state machine diagram, the states are these circles here, and they usually have a label, so we can tell that our 2 states are even number of zeros or odd number of zeros. I'm just going to say even or odd. And these arrows here that go between the states and back to themselves are the transitions, and the 1s and 0s that are characters in our alphabet label the transitions. So say we're on the even number of zeros and we see a 1, we're going to follow that arrow, and then we're back at even number of zeros. So if we look at some examples, if we look at example A, we got 0, 0. So we start at even number of zeros, we get a 0. We're at the odd number of zeros, we get another 0 again, we follow the arrow, we're back at even. Pretty simple. I'm just going to skip the other examples. I also came up with a simple code example because I know a lot of us are programmers. It's a bit more tangible. So here we have an object, transitions, and the keys would be the current state, and then those are also objects, and then their keys would be the input character that they see, and their value would be the next state. And then you can see below that we have our states, our start state, our input symbols, and our transition function, which just takes the state and the input and returns the state from the object. And just as an example from code, we have our sequence of input characters, 0, 0, 1, 0, 0. And we go final state, and then we use the reduce method. Who's not familiar with reduce? I guess, okay, so yeah, reduce starts with, reduce is usually used for accumulators. So say you need to sum a list of items, you could use reduce. It's part of kind of the family of filter, map, and reduce. Map would take the array of input, like our sequence, and it would map it to like an array with the same amount of items, whereas reduce reduces it to 1. Therefore reduce. So here we pass in our transition, which is our transition function. So on each of our items, it's going to run this transition function, and our start state will be the initial state of this reduce. So as it goes over, it'll start with the start state, pass the start state and the first element of our sequence into the transition function, and then that'll become the accumulator in reduce. And then it'll eventually give us even. I didn't prepare to live execute this, but you get the idea. So I want to go into kind of a more tangible example. That's all in code, but let's get into something real world. So the example I came up with is a country road stoplight system. The importance of the country road is that there's not much traffic, so you don't need that much complexity. So you see my little legend here. I didn't even notice the screenshots I have there have my cursor. Sorry about that. Well, we can just ignore those. Those aren't part of the legend there. So the little blocks in the gray is the road. So we've got a horizontal running road, a vertical running road, and we got arrows that say the directions of the traffic. And then the boxes in the middle are the stoplights. So the blue stoplights are the stoplights for the horizontal road, yellow are for the vertical. So let's make a state machine for this. But first, I kind of want to tighten this up a bit so we know exactly how to go through it. How do we know which stoplight should be green, which one should be red? There's going to be a weight pad at the intersection. So at the tip of each arrow, there will be a weight pad. If a car is there, it'll trigger an event and say, hey, there's a car here. There's no pedestrian crossing, so there's no complexity there. And the stoplights, there's no yellow. They're either green or red, just like on or off. Only one light's green at a time, so if the horizontal light's green, the vertical one can't be. And if no weights are activated, we won't change the lights. And if there are vehicles in both directions, meaning both weights are activated, we'll let the horizontal direction go first. So this transition table is a way to visualize the transitions within your state machine. So we can see in the columns there, we've got the states. So we've got our horizontal green and our vertical green. And then in the row there, we got our input. So either both weights off, horizontal weights on, vertical weights on, or both weights are on. I won't get into the transitions, but you can see they're there. And then I made a diagram for this. Again, the curves are not pretty. It's something I hope to improve. So I tried. Thank you. Thank you. So yeah, we start off with horizontal green. And then if both of them are off, then we go back to horizontal green. We stay there. And then if the vertical weight's on, then we go to the vertical green. If the horizontal weight's on, we go back. And then if we're both on from vertical green, then of course we go back to horizontal green. So I'm just going to go back to the transition table for a second. So you can see here we have 2 states and we have 4 inputs. So in a DFA, we need to model all 4 inputs for every state. So we should have a total of 8 transitions here. In my future slides, I'm going to slim this down. So you see how both on, horizontal weight on, and both off all go to the same one. We're just going to combine those. So this is a simple state machine. There are only 2 states. We don't have much time, so hopefully that kind of gave you an idea of how to change stoplight state. We'll get into a bit of pattern matching. So our goal now is to find a string with at least 2 zeros and 2 ones. So now I'm using the mathematical notation for the first time in the slides. I chose this amount of states here. You'll see why when I have the diagram. Our input alphabet will just be zeros and ones. Our transition functions, it'd be too long to write, so we'll just look at the diagram in a sec. We'll start off with the A state, and when we've seen 2 zeros and 2 ones, our accept state will be the I state. I just called them A through I because I didn't want to call them 2 zeros and 2 ones and such. So you can see here, we're trying to keep track of 2 things with the state machine. We kind of want to have a counter of zeros and ones. This is the easiest way I can model it as kind of like a matrix. So whenever there's a 0 transition, it goes off to the, or whenever there's a 0 character, it goes off to the right. A 1 character, it goes down, just for easy readability. And you can see there, let's say we have a 0, 0. Oh, I forgot to label a few. Sorry. Sorry. Yeah, down's 1, right's 0. It's easy enough to remember. And then you can see there, once we've seen enough zeros and enough ones, at our accept state there, I, which is denoted by kind of the double circle, that's pretty standard. If we see any more zeros or ones, we'll repeat on the same state. So, okay, we can count 2 zeros, 2 ones, no problem. If we know what we want to count, we can use a state machine for it. But why would we not use a state machine? Well, we can't use a state machine to determine whether a string has the same number of zeros as it does ones, because there's no way for us to count within a finite amount of states how many zeros or ones we've seen so far. I'm not going to get into this at all, but I think this is the pumping lemma or something. So if you want to look into that, go to the pumping lemma, or if anyone wants to talk about that after, please, because I'm not going to go into that. And then another cool application of state machines I've seen is the Markov chain. So it's not a deterministic state machine, it's a stochastic state machine, which means there's the transitions between each state aren't defined as clearly as they are with, say, this. We see a 0, we go to the next state. We see a 1, we go to the other state. But with a Markov chain, we have a probability associated with each transition. So each time we want to go between a state, we generate a random number. If it's below 0.4, we'd go to that top one. If it's above that, we'd go to the bottom one. So Markov chains are commonly used in natural language processing, or even on your keyboard. If you know when you type on your keyboard and it gives you words suggested based on what you've written before, this is what it's making in the background. It's determining the probability of each word that you've written and the probability that you write it again. Yeah, so that's Markov chains, and that's it. Any questions? Yep.
So could Markov chains then be used for like procedural generation as well, or is it really just an NLP thing?
Definitely.
Really? Cool.
Yeah, I think so.
Oh,
Not that I've done it, but I'm sure you could do it. Cool. Cool.
I'm trying to formulate the question. So I'm seeing, again, like it was triggered by the Markov chain. So that would be how like most like text prediction works, I'm presuming.
Yeah, exactly. Even this diagram I pulled from a Quora article where it was talking about Swift key, which is one of the first kind of text prediction things they use on the phone.
Between a state machine and just a graph, what that is. What would differentiate between a state machine and a graph or a tree, like a bee tree?
It is.
Yeah, it is a type of graph, but like, so.
Yeah, a state machine has like a defined execution order on this graph.
Okay.
Whereas your graph could be interpreted in multiple ways, but as a state machine, it's kind of defined.
So then the Markov chain would kind of be like you would use use that as input into the state machine then? Or you pass that to a state machine to figure out which node on the chain is the correct node?
It is a state machine. It's just it's stochastic rather than deterministic. So, for example, let's say we had the whole text of Alice in Wonderland, and we wanted to write a novel just like Alice in Wonderland. We could parse the text, determine the probability of each word coming after the word before it, and then we could take that graph and then generate text saying, okay, we're at this word, we generated this number, based on the probability, what's the next word? Cool, awesome.
Okay.
You have a question? Yeah.
I think one thing that might change this up, if these are going on probability, say you go down to the IM, it makes the probability there.
Sure.
Essentially, that whole I love branch is now gone. No one, you're never worrying about those branches of state anymore.
Yeah, I mean, it really depends on how you program it, but what if it goes to I am something and I, and then it could continue, then you can kind of loop back into that. I don't know if you've ever
So
hit
that's
like the
starting
same
node.
thing.
I isn't necessarily a starting node, they're just a node.
It depends. Yeah. So it could, so exactly. Yeah.
Cool.
Awesome. Thank you.